Good morning. Here are the notes for 2.5, all about the fundamental theorem of algebra. You'll learn how to determine the numbers of zeros of polynomial functions and to find them. So you've heard me talk about the fundamental theorem of algebra before, I believe, and that's really just an nth degree polynomial has n roots. And the linear factorization theorem, it's kind of the same thing. An nth degree polynomial has n factors. That's how we get the n roots. And then conjugates, I believe what they're referring to is in the imaginary system. I'm trying to think of a short way to write this, but in the imaginary system, if a plus bi is a factor of a polynomial, then its conjugate, so a minus bi, is a factor. So imaginary roots or factors come in pairs. Okay, so let me fill in some blanks here. In the complex number system, every nth degree polynomial has n roots. How many zeros does this function have? Well, it's 5 minus 2x squared plus x cubed minus 12x to the fifth. So the degree of this polynomial is 5, so it has 5 roots. And it's going to have, this would have 5 factors. An nth degree polynomial will have n number of factors. Okay, so they had us define everything and then define it again. So now let's go ahead and do some work. So in section 2, finding zeros of a polynomial function, remember that the n zeros of a polynomial functions can be real or complex, and they may be what? Oh, repeated. Yes, I was thinking of multiplicity, but I couldn't figure out how to fit that in the blank. So if we have a multiplicity of more than 1, then we just need to count those towards our total number of factors. So we want to list all the zeros of this polynomial function. So this is where I can use the rational root theorem because, well, you know what? I'm going to just see if I can factor this thing by grouping. So if I pull out an x squared, I get an x minus 2, and here I pull out a 36 and I get x minus 2. Oh yeah, so I can do x squared plus 36 times x minus 2, and so 2 is one of the zeros. And then I don't know if you guys recognize this right off the bat. This is kind of a famous non-factorable pair. Like whenever they're teaching difference of squares, you always can factor it if it has a difference, but if it's a plus, then it's non-factorable. So now let's go ahead and just see what the zeros are of that. So I'm going to set x squared plus 36 equal to 0. I'm going to jump the 36 over. So if x squared is negative 36, when I square root both sides, that's where our imaginary numbers come in. So the square root of negative 36 is just plus or minus 6i. So we said that if you have an imaginary number, then the conjugate will be a factor or a zero as well. So here are our 3 factors. It's a third degree polynomial, 2 and plus or minus 6i. So if a plus bi, all right. I've already answered that. If a plus bi is a factor, then a minus bi is also a factor or a zero of the function. So when we're factoring a polynomial, to write a polynomial of degree n is greater than 0, it'll be the the product of linear and quadratic factors. Sometimes our quadratic factor will have the two complex roots, so that's why we include those. A quadratic factor with no real zeros is said to be, we'll call it prime. The book calls it irreducible over the reals. So even though it has imaginary roots, if it's prime or irreducible, unfactorable, these are some terms we would use. So now let's take a look at this polynomial we're given in example 3. And I'm seeing that it's following a number pattern that's similar to a quadratic, except we've got x to the 4th, x squared, and 36. But something tells me this is going to factor like this, x squared and x squared. So if I find two things that multiply to equal negative 36 that add to equal 5, I know that 9 and negative 4 are going to fit the bill. So here I have a positive 9 and here I have a negative 4. So this guy is going to factor right off the bat. That's a difference of squares. Hopefully you can recognize those. And then this x squared plus 9, those are going to always factor in the same way. X squared plus 9 equals 0, x squared equals negative 9, x equals plus or minus 3i. So I got that by square rooting both sides. So the factors, so these are my zeros, so the factor is x minus 3i, x plus 3i. So I've got 4 factors, 4 zeros. I'm fitting into the fundamental theorem of algebra. Explain why a graph cannot be used to locate complex zeros. So they don't cross the x-axis. So this thing is x to the 4th. If I was going to sketch that, the leading coefficient is positive. 2 of the zeros are at 2 and negative 2. So I could plot this here, and we know it's up opening on both sides. So basically what happens is with that imaginary 0, the hump that's created by those factors, it just doesn't go all the way up and cross over the axis. So that's that for section 2.5. Thanks for watching.